Hi, I'm Tom Mitchell from the Creative Technologies Lab at the University of the West of England, and I'm presenting this paper on behalf of my co-authors, Don Brown and Chris Nash. As the title suggests, in this paper we present a pilot study that explores digital musical instruments that are prone to error, and a particular focus is gestural musical instruments. Now, errors, mistakes and failure are a key component of musical practice and progression. Musicians become proficient in their instruments by recognising and correcting their errors. Players learn from their mistakes, and failure is often recognised as the consequence of striving to succeed. One of the joys of going to music concerts is observing fluid and expressive renditions of music at close proximity. As Hazard and colleagues have previously described, witnessing skilled performers undertake a difficult challenge adds to the frisson of live performance. The assessment of musical skill is complex and of course subjective, but a key factor is the ability to perform without error. Gurevich goes so far as to describe musical success as the inverse of error, and in previous studies the frequency and severity of performer-related errors are used as indicators of skill. Now, the types of error that I've described so far are what we refer to in this paper as performer errors, errors that take place when a player's actions do not align with their intentions. This type of error is referred to as a slip in James Reason's seminal analysis of human error. We should stress here that errors are certainly not always considered negatively in music. Performance errors are often embraced as an inevitable consequence of exploratory performance that can open creative opportunities for musical progress. As Scott Adams famously stated of the art more generally, creativity is allowing yourself to make mistakes, art is knowing which ones to keep. Similarly, indeterminacy has and continues to play an important role in contemporary music. Cage used an abstract notation in Concert for Piano and Orchestra to provide space for performer improvisation, and Xenakis used stochastic processes to compose Pitha Prakta. Indeterminacy and chance have also been a long-standing feature of performances with new musical instruments. For example, Chadabi's echoes and Dystart's pencil fields both incorporate elements of indeterminacy, where unexpected changes are viewed as creative input from the instrument. In these examples, indeterminacy is intentional and measured. However, performances with experimental and prototype DMIs, or digital musical instruments, are frequently disrupted by unintended errors owing to some form of technical failure within the instrument. Many DMIs are handmade by their players, and rarely are they subjected to extensive testing and design iteration. Consequently, they can include some technical vulnerabilities, where a player might correctly articulate their intention, but the instrument misinterprets their actions and responds incorrectly, or sometimes not at all. Here we refer to these types of errors as system errors, as distinct from the performer errors that we described earlier. Gestural DMIs that use machine learning techniques are particularly vulnerable to system errors, as noise in the motion capture system combined with poor training data can lead to unpredictable mappings. When these algorithms are used for classification, recognition accuracies will always fall short of 100%, and this makes system errors an almost inevitable feature of performances with gestural music instruments. For some time now, we have been developing a glove-based gestural performance system in partnership with Mimi Gloves Limited. The system enables musicians to define their own gestural mappings using machine learning techniques, and is now actively used by hundreds of performing musicians and media artists. In the majority of cases, indeterminacy in the action-sound mappings is perceived to be undesirable, and in a previous study that we published in Digital Creativity, gestural misclassification errors were identified as a problematic feature of the system. We're interested in understanding how these system errors affect a musician's ability to perform music, and how system errors affect a musician's perception of their instrument. To investigate these questions, Dom ran a within-group study with 5 participants using our data glove-based gestural music system. After familiarising themselves with the instrument, participants were asked to perform 20 repetitions of the music, as shown here. The task was repeated 6 times, with intentional system error introduced at 0, 1, 2, 5, 10 and 20%. To minimise carryover effects, the order in which participants were exposed to the different error rates was randomised. System errors were introduced when a participant selected to play a note, where at a rate of 0%, no deliberate errors were introduced, and at 20%, on average, 1 in 5 notes was played incorrectly by choosing a different note at random from the score. With no established convention for performing note selection with mid-air gestures, we drew from the practice of our existing glove users, as observed in previous studies, selecting a mapping that would minimise the occurrence of genuine system errors. A point and grab metaphor was chosen where notes were selected by aligning the hand with an axis of the system's coordinate frame, i.e. by pointing up, down, forwards, left or right, and triggering note messages with a fist posture. To further reduce the occurrence of genuine system errors, we disabled the machine learning components of our system, which is normally used for posture recognition. Instead, the grab posture was engaged when a threshold on the proximal flex sensor of the middle finger was exceeded. For each note in the score, the timestamp and number of the precisely quantized reference note, performer selected note, and the note emitted by the system were all logged for later analysis. This enabled performer and system errors to be easily disambiguated. For example, if our reference note is a note E3, which is selected correctly by our player and emitted correctly by our system, then the only error measured here is a performer timing error of 16 milliseconds. However, if our performer makes a note selection error, where our reference is note D3, and the player instead selects note E3, then we recognise that there's a performer error. If there's no system error, then the selected note is emitted correctly. In this last example, if the reference note is C4, which is selected correctly by our performer, but a system error is introduced and instead note G3 is emitted and heard, then we have an example of a system error. So let's have a look at the results. We'll look at the performer note timing error first, which indicated a statistically significant increase when we compared our controlled condition of 0% error with the 5, 10 and 20% error rate conditions. The performer note selection error results were not so clear-cut, with no significant difference observed between the control condition and the other error rate conditions. However, a significant increase in note selection error was observed between the 2% error rate and the 5 and 20% error rate conditions. Although the number of participants in this study was small, the results do suggest that as system errors increase, the prevalence of performer note selection errors and the severity of timing errors also increase. That is, players are more likely to make mistakes when the instruments they use are themselves prone to error. To some extent, this observation could be considered axiomatic. The importance of accurate feedback in machine control, and in particular musical control, is very well established, and any disruption to the action-perception loop invites the potential for uncertainty and error. Perhaps more interesting are the results to the qualitative measurements which were recorded after each test condition and were designed to capture the participants' subjective experience at the different rates of system error. These took the form of 3 10-point Likert scale questions relating to the perceived responsiveness and accuracy of the system, along with the player's sense of control. These results clearly indicate that in the presence of any error, the system was perceived to be significantly less accurate, less responsive, and led to a reduced sense of control. The most significant drop in these perceptual factors occurs between system error rates of 0 and 1%, an effect that appears to plateau as the rate of system error is further increased. This finding suggests that musicians may well have a very low tolerance for error, and if these results are indicative of DMIs more generally, the findings present an important consideration for instrument designers. When precise control is desired, then every effort should be made to eliminate system errors. This underlines the importance of rigorous testing of algorithms, processes and interfaces, as well as iterating designs in collaboration with players. The study also highlights the importance of achieving high classification rates when machine learning algorithms are used for gesture detection in music systems. Informed by this work, we intend to conduct a follow-on study with a larger number of participants performing over a longer period of time with a reduced number of system error conditions to explore the effects of system error on skill acquisition. This will take the form of a between-group study in which each participant will perform at a fixed error rate.